Okay, so first of all, thanks for having us. Yeah, today I will talk a little bit about Acurast and how we are planning to build the largest cloud, basically the largest decentralized and serverless cloud. So first, let's do a small introduction. The problem with the current cloud providers that exist are manifold. So the first of all, they're very expensive. There are kind of monopolies in the space, and that really drives up the price because smaller companies can't really compete with big companies like Google and Microsoft and Amazon. So there's not much competition going on. The second problem is that it's intransparent. It's not really clear regarding the pricing why things cost a certain amount, and that's something that we would like to change. It's also very centralized. Most of the providers, they're US based, so there are certain laws, and well, just in general, it's centralized, and you don't really have any alternatives to it. And last but not least, it's not confidential. So you basically have to trust that the cloud providers don't look at what you're doing and the data that you have on your cloud servers. And those are the things that we try to tackle with Acurast. Now, new chips are changing the game. Mobile phones, or specifically the chips that are used in mobile phones, like the ARM64-based chips in, for example, the Google phone, they really kind of upped the game regarding computing power. So, because if we look into a chip, then there is not only a CPU that we generally have in cloud computing servers, but we also have a GPU with 20 cores in this case. We have a specific chip that does machine learning, and some other chips that help with like specific tasks that are not generally available in cloud computing services. There you usually have to get way more expensive special instances to support these tasks efficiently. So if we compare, for example, like a server rack or a server that you can buy with a mobile phone, the Google Pixel in this example, we can see a couple of differences. So first of all, the price. The mobile phone is 6 times cheaper than the server. But at the same time, as you can see, just the CPU benchmark alone is already faster than on the phone than it is on the server. But this doesn't even take into account the other chips that exist, like the GPU and the TPU I talked about before. If you factor those in, depending on the tasks that you want to run, you can get like a 80% higher kind of performance. And this kind of this higher performance, you would think it comes at a higher price of energy, but that's actually not the case because those newer chips, they are way, way more energy efficient. As you can see here, they take about 50 times less energy. And that, of course, results in an overall better performance because you could, for the same price, have many, many more chips running your code. And then there is one more very important use case, which is you can upcycle old cell phones, because to run, to participate as we call them processors in our network, kind of the server in our network, you can basically you don't have to buy a new phone. You can get an old phone off of eBay. It may even be one that has a cracked screen or some other problems. As long as the camera works and the CPU still works and it has the network access, you can participate in our Acurast network and provide the compute power. And this, of course, these phones, they're sometimes very cheap. You can go as low as $10, as we can see in the screenshot. So that's a really nice way of reusing old hardware for modern cloud. Now, there are people, anyone can actually become a processor. You don't have to be special person. You can just buy a phone and join the network. Onboarding takes about 3 minutes. You basically just have to scan a QR code on our website, and then the whole setup process, it takes a few minutes only. It requires no technical knowledge. You just have to go through the setup steps. And with this, we can see how people are starting to build kind of small little device farms. And they are basically what drives the Acurast backend, so to speak. Yes, so if we take everything that we talked about and compare it together, then you can, if you take a comparable or I think this is a Google instance, it would be around 30 times cheaper to run it on the Acurast network. And that's only regarding the price. You, as I mentioned before, also get the benefits of having confidential computing. And we'll talk a little bit about how we do that in a bit. So this overview looks quite confusing. So the important things here are that Acurast is its own layer 1 protocol, and it's a permissionless system, and you can access the compute through the Acurast orchestrator, which has like a matching engine and a reputation engine, and it handles the billing. And all the executions that run on the Acurast platform are completely confidential, and the results are verifiable. Yes. So I think I won't go too much into detail here because now we are going to do a live demo, so you can actually see how this is going to look. Okay, so let's get started. So first of all, you can, if you want to use as a developer, if you want to use the Acurast network, then you first have to go and get some Acurast tokens. You can do that by using the faucet. So you just enter your address, you have a tweet about it, and then you get your free tokens. So now in this example, we'll actually use we will deploy a contract, and then we will deploy a job, which is what we call like the code that runs on the Acurast network, and we will check the results that are reported back. So here we have a very simple contract. It's basically kind of a simple Oracle contract. It has like a method that is used to add data to the contract. Like of course, only the people that are allowed. So we have an allow method where the admin can allow certain users, certain processors to add data to the Oracle. And then we also have like a method to view the current state. So I already have my Talisman wallet set up with a couple of Acurast tokens and a couple of testnet tokens. So now let's go here and actually deploy this contract. I've already deployed the contract, so we'll just say Acurast demo, and then here I can take this contract, and we can see we have the same methods as before, and now we can deploy it here. Okay, so contract is deployed, and now we can head over to Acurast and actually run a job that will then post the results to this contract. So in this case, this is demo code from before. So let me refresh the page. So in this case, we select our 0 here, and then we use the price feed example. So we already have an example set up that calls the Binance API and calls some gets some price. Let's use the Bitcoin and USD price. So we'll change that here. And then also the destination is, of course, the contract that we have just deployed. So let's replace that here. So basically what this code does, it it does an HTTP request to the URL, and then the response is kind of the numbers are converted, and then it is getting sent as a transaction on the LF0 network. Good. So the code here is okay like this. So now we can, to create this job, we have to set a couple of parameters. So I have prepared, now it's, okay. So here, for example, we have, this contract is now no longer valid, but I will use a specific processor in this case, just to make sure that everything works. So here we say we run this code on a specific processor, but you could also use a public processor that would do the same thing almost. And then we select the start time. So in this case, because we have to do a couple of things in between, I'm going to select, I'm going to say it should start in 5 minutes. And it should run for then 5 minutes. Then we set the interval to 1 minute. So this results in 5 executions, and we can leave the duration and the delay. And then here we set a small reward for the processor that actually executes this job. And then we can publish the job. We have to, of course, sign the transaction. And now this will take a little while. It will, basically now the job has been posted to the network. And now the matcher that we have, it will kind of match the requirements that we have with this job to a processor that provides these things that we need. In this case, because I selected a specific processor, the matching is very fast. Usually it takes maybe 30 seconds for the matching to be done. Now the processor has been notified, and it has to acknowledge that it wants to accept the job that we have just posted. So let's quickly wait for that. Yeah, so that went well. And now we can go to the job. Now, we have to quickly wait here a little bit. It's, internally, I'm not quite sure why it's taking this time, but we basically have to wait now to see the address of the processor. And one important thing is that this processor usually does not have any funds on the LF0 testnet, but it of course needs funds so it can actually post the results to the chain. So here we copy the address, and then we head over to the Polka.js, and I'll transfer a couple of, I mean, I actually did it in this case already, but I'll just still do it for you to see. We transfer over a couple of funds, so it is able to pay the transaction fees to post the results of the API request to the chain. And also, as mentioned before, we have to add this processor to the allow list. So I'm going to add it here. Good. So now we are basically waiting for the time for the processor to start. So, well, that's going to take 3 minutes. So we have to wait for 3 minutes. During that time, yeah, I can maybe talk a little bit about the kind of a little bit more technical inner workings and the confidential computing, because it is possible to so it is possible to, each processor has its own key pair. So it is possible to encrypt the code that you want to run, or the data more. I mean, usually it's more the data that you want to protect. You can encrypt the data, so only that specific processor that has your job assigned can actually decrypt the data inside its secure enclave, like the secure processor that it has. So that means, and then the code can work with this decrypted data and post the result to the chain. Now, the cool thing about this is that nobody, not even the owner of the person that physically has the device in his hands, is able to read this data out, because it all happens in this secure chip. So the encrypted data does never leave this secure environment, and that's actually a very cool feature of the Acurast network and these processors. Okay, so yeah, we're almost there. We basically now are waiting again for the time to hit 18 past, and then it should execute once, and we should be able to fetch the price. I think I'll already prepare this. So in order to get the price, I think we used, actually, I did encoded it wrong here, because I have to do a hex encoding. But now we can actually, and this is, I'll talk about this more later. I now have to, I'll quickly just have to convert this string to hex. I'll do that here. Console, and then that's the right ticker. Yes. Where was I? Here. Okay. Okay, so let's go back to the jobs page. We see here it's still in progress, but we now have 1 of 5 executions. So let's cross our fingers and let's go back to the contract and check here. And as we can see, we have successfully posted the result of the API request on chain, and we can now see the current price of Bitcoin to US dollars that matches this price here. Oh, and it looks like while I was testing 2 hours ago, it went down $2,000. So yeah, so that's basically the first part of the demo. So I hope this was kind of understandable. So you can create your, with JavaScript, you can create your jobs, and then you can post them to the Acurast network with some parameters, and then a processor will pick it up and execute it for you, and put the result on chain to your contracts. Now, one thing that we have noticed while we were developing, and also today we saw this, to debug and test like quickly stuff, it's actually a little annoying to wait, like in my case, these 5 minutes. It would have been nicer if we could just immediately get the result. This is why we set up what we call a live coding feature. So what this basically does is you can, without going too much into details, you can deploy a job to a processor that has a WebSocket connection open, and then you can send code to that processor through WebSockets, and then it immediately evaluates it with eval and sends you back the response. So that way, it's way simpler to, or faster to debug. So here we can actually try that out. I can select this processor here that I have previously set up, and now I can run the code. So first we connect to the server, and now fingers crossed that this works. Let me quickly refresh. Try again. Oops. Okay, and try again. It's possible that and there we can see we get the result down here. So basically what happens, as I just explained, there is a processor now running this WebSocket code, and it's basically just there waiting for instructions to be sent. Then it executes the code and it sends the result back. So we can also use this to debug our code and test our code. So let's try to do the same thing. with the code that we used before, but this time we use Aave that we have here, a preset, and then we again need the contract code. Maybe just to kind of show that it really works, we check what the current price is in the oracle for that other pair, so that doesn't return a result. And now we can go here. I don't remember if I copied the contract. So we have the right contract, Aave USD. Okay, so now we can basically run this code on the processor live, and the success is undefined because of it basically just prints what the return value is, but there is no return value here. So let's wait for a second because it should actually, no, I think it may have already worked. Forgot to change the prints here to logs, so we get the console logs back here. So then we head back here, and if all went well, which apparently did not, should have updated the price here. Okay, so that's unfortunate. Let me try again. Like this, we should get some debug information. So let's run it again. Yeah, so it did succeed. Maybe, I don't know, I'll quickly try to refresh this page. Okay, I remember before, I think there was, I made a mistake because I didn't use the correct ticker. So let's again convert this quickly to hex. And now we can actually, just for fun, we can not do it in the console, but rather we can do it on the processor. So here I can do return 22 hex. So then I run it, and the processor gives me back the hex. And yeah, I can just head over here. Okay, so that didn't seem to work, but at least the first one worked. So in theory, I'd have to debug a little bit afterwards what the issue was. In theory, that should have worked the same way as the first example that we saw, but kind of easier because now you can just play around with it and change the parameters and so on. Now, this is kind of the use case of an oracle. There are other things that you can do with this as a small showcase, which kind of shows how you can use this confidential execution feature to, for example, run a game. So in this case, it's not going to be that impressive because it's just all going to happen at once. But you can imagine how you could split that up and make the logic a bit different. So it's actually an interactive example. Yes, someone just told me that the reason why it didn't work with the live example was actually because I didn't add this live code processor to the allow list. So that's why the transaction went through, but it was rejected because I wasn't an owner. So actually now to verify that this is the case, I can actually go here and because I'm running this specific processor locally here to have some debug information. So let's go over here and to allow, and here. Okay, let's go back here, select the example again, change the destination. And cross fingers again that this time it worked. Okay, so let's now we have to get the thing again. Yeah, okay, cool. So it was actually user error as always. Okay, Cool. So I'm glad that worked. So coming back to the example I was talking about before, so you could basically run games, for example, on a processor, and then have an interactive interface through WebSockets where people can play, where you know that nobody knows what the state of the game is, and nobody is able to cheat, because of course you can verify the code that is executed on a processor. By the way, that just to show that it's basically, if you go to a job, you can the script is going to be on IPFS, so you can see what the script is, and then all the participants can verify that there is no backdoor in the code, and then you could run a game. And we have such a we found a game, a poker engine online. So this is just a random JavaScript project, and we can actually copy the whole code here. It's, I don't know why it doesn't copy. Or scroll down, so I'll go down here. I can copy all of this and go back here, paste it, and now it's basically here is the whole logic of the poker game, and down here you have some steps that the players are taking. So it's like you initialize the game, you add some players, you start the game, and then you bet a new player joins. And of course, now this is kind of all happening sequentially. So let's hope this works. And so we can see how the game was executed in the secure enclave of a processor where nobody has had access to the state. Now, again, this is kind of a boring example because there's no interactive part to it, but that's because the WebSocket code that we deployed on this processor is meant to kind of isolate each execution. But you could imagine how you would basically set up the game itself, and then have a WebSocket connection where every player could play when it's his turn, and in the end you get the result where you know that nobody has tampered with the result. Yeah, I think that's it. So thanks a lot for your attention. I don't know if there are any questions. I'm happy to answer them. I think I will go back. Yeah. Yes. So now I can see. This works with Raspberry Pi as well. So I'm assuming your question is if you can use a Raspberry Pi to join the network, and the answer is no, because we rely on the secure enclave of the device to provide this confidential computing. If you would join with a normal device that does not have a secure chip, then it would be possible that people could kind of inspect or even change the code that is being run, and that would kind of compromise the security and the integrity of the system. Yeah. Okay. So. Yeah. So actually, I have one more slide here, which is the outlook. So one thing is this is what I showed you is now kind of the level 1 integration of Aleph Zero. We are working on the level 2 integration, which means that you do not have to fund the processor. Like in this one step, I had to send funds to it. So that would kind of be abstracted away, and it would be made much simpler if once that is ready. And also there's the Acurast Builders program, where you can start building with Acurast and earn the CAcu token, which is our testnet or our canary net token. So we'd be very happy if you join there. Yeah, so that's it. Here are some links how you can reach out to us. We're very happy for all the follows that you can give us and the upvotes on social media. And we're also very happy for feedback. If you test our system and you find something confusing or something doesn't work, then feel free to reach out to us. we're very happy for all the feedback and responsive on social network. If you have any questions.